The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Hello and welcome to Science for the People. On today's episode, we'll be talking about a few things that the world might be running out of and what that could mean to you. Later on in the show, we'll be talking to Moses Chan about our helium reserve, or lack thereof, and to James Elser about what would happen to us and to the world without phosphorus. But let's start off with metal. Hello and welcome to Science for the People. I'm joined by Thomas Graedel, Clifton R. Musser Professor of Industrial Ecology at the School of Forestry and Environmental Studies at Yale University. His research is centered on developing and enhancing industrial ecology, the organizing framework for the study of the interactions of the modern technological society with the environment. His textbook, Industrial Ecology and Sustainable Engineering, co-authored with B.R. Allenby, was the first book in the field, and it's now in its third edition. Welcome to the show, Thomas.
Thanks very much.
Now, a few months ago, you authored a paper on the criticality of various metals. So what do you mean by criticality?
It's a term that has been debated a bit among the people that are interested, but basically what it reflects is the sense of materials that are in some sense important and at the same time under some availability challenges. So the idea is that if you need a material to support modern technology, modern defense applications, anything you regard as highly sensitive, and you can't get that material in sufficient quantity at sufficient price, then it is in some degree critical. And the way this is measured has been evolving over the past few years as the evidence has been increasing. I think that as we use more materials all the time and a wider range of materials all the time, there is some level of probability that we are going to see some shortages in the next several years, and we're trying to figure out where those might occur and how serious they might be.
Okay, well, maybe can you run us through the study? You made a list of 62 elements that were important to technology. So important how?
Perhaps the most interesting statistic that I know is that a modern computer chip requires, for its manufacturing and performance, somewhere between 60 and 65 different elements, which is almost everything in the periodic table that is not radioactive or a noble gas. In other words, we really are using almost everything these days. So the idea of substitution takes on a different character when we say, if we're using everything, what are our options to ever use anything different when we've selected these materials very specifically for their physical and chemical properties, their corrosion resistance, or their conductivity, or the degree to which they can serve as a colored phosphor on a display screen. So in a sense, our technology, by selecting the most perfect materials for applications that really stretch the boundaries of technology, mean that we limit our opportunities to deal with situations of shortage because we don't have a lot of opportunity to move from one structural material or one physical material to another, because doing so would almost surely result in a decrease in performance.
But the uses were actually fairly difficult to determine for each element, weren't they?
It depends on the element, I would say. For the elements that are widely used, copper, iron, zinc, we know very well, the engineering community knows very well what uses are common and roughly how much of a year's extraction and processing of those materials go into those major uses. For the elements that are used in much smaller quantities and in much more diverse applications, elements with names that aren't familiar to a lot of people like dysprosium or selenium, we had to do a substantial amount of research, telephone calls, conversations with a lot of different people to establish their major uses and how those have evolved over time. This is always an evolving situation, but I think we probably know that about as well as it can be known at this stage of the game.
I was thinking specifically because the companies that use those metals and in what proportions are quite often trade secrets, correct?
That's correct. And so as we've talked to people, we have had some people realizing that we are trying to provide information that is of general use. We've had people say, I will give you my best estimates, but I don't want to be quoted on them. And if we talk to enough different people and read enough different pieces of literature, we feel we can get at least a good first approximation of the major uses of the whole suite of metals. And often an approximation is quite sufficient to get a general idea of the situation with any of them now and some idea of where things might be going in the next decade or so.
Well, how did you figure out what substitutes might be available once you figured out what the specific elements were in their uses?
Most of the elements have 4 or 5 principal uses that account for 80 or 90% of their total use. So what we decided to do was to not try to track down the last 1 or 2 or 3% of the uses, but to take the uses that constituted perhaps 80 or 85% of the use of a particular metal. And then for each of those uses, the best substitute could tend to be a different material. If the principal use involves conductivity, then we look for a substitute that also has good conductivity. If it is more of a high temperature corrosion resistance, then we would look for a substitute with those properties. And we went through all the elements and all their principal uses, identifying the best substitute in each case, often with a lot of help from people we talked to in industry. We then said, well, how good is that best substitute? Is this something that if you made the substitution, it would be as effective as the original just about, or would it seriously compromise performance? And on that basis, we were able to come to a determination of the degree to which substitutability is feasible for all of the elements that we were looking at.
When you looked at a number of other aspects of the elements as well, you created a 3D map where you represented supply risk, environmental implications, and vulnerability to supply restrictions. Can you talk a bit about that?
The determination of criticality for an individual material certainly has to do with the risk that you can't get it. And so in trying to determine that risk, we and others that have looked at this property of the materials, we certainly look at geological factors, how much is in the ground and what are the economic and technological challenges involved in getting it. We also look at geopolitical factors. Might the principal mines for a metal be located in a country that, rather than freely exporting, would like to reserve the material for its own use? So there are various factors that come up in whether you can get the metal. That's the supply risk part of the parameter. The vulnerability to supply restriction measures much more the target user. If you are a manufacturer that needs that material, then it's going to be more critical for you than if you are a manufacturer that doesn't use that material in the products that you make. The vulnerability is also the issue where substitution comes into play. If substitution is a reasonable possibility, then you're much less vulnerable than if you have a material that's difficult to substitute for. And then finally, the environmental considerations tend to involve two different properties of metals. One is whether they require a large amount of energy in order to extract and process them, and hence a potential climate change impact. And the other is toxicity, which doesn't apply in the case of many metals, but there are a handful, probably 5 or 10, for which there is a significant amount of toxicity, and that's another consideration that one wants to think about in terms of the use of those materials. So we combine those three rather intricately measured attributes of the metal to achieve our assessment of the degree to which it is critical or less critical.
So then what was the assessment? What were the results of your study? What did you find out?
In the case of substitutability, which is one part of this activity, we found about a dozen metals for which no exemplary substitutes appeared to be available for any of their major uses. So in those cases, these are elements that we really have to have unless we completely change our technology. These are elements like rhenium used in jet engines, manganese used to make steel, and a number of others. Perhaps even more interesting is that for none of the 62 materials that we looked at could we find exemplary substitutes for all of their major uses. In other words, we think that there is no metal in the periodic table today for which we can just substitute every time that we have a major use for that metal. So this says that for modern technology, right now, we need everything because we do not have any material for which we have drop-in substitutes across the board of the major uses.
This is Science for the People. I'm here with Thomas Graedel, Clifton R. Musser Professor of Industrial Ecology in the School of Forestry and Environmental Studies at Yale University. And we're talking about the metals that are used in all of our gadgets and whether you should be worried about them running out. Because that sounds vaguely terrifying, Thomas, to anyone who is highly dependent on technology. And honestly, at this point, that is pretty much all of us. So what does all this mean on a practical level, that there aren't substitutes for these materials?
I think what it means is that we need not to think about making simple one-to-one gradual transformations in the products that we depend on to move them slowly from one material to another because we don't have those materials that will enable them to maintain their performance. We really need to think of transformational technologies that move us into a different realm of technology. For electronics, for example, there are signs that we can move away from dependence on a wide range of metals into the use of organic conductors and other materials and other processing developments that require either much less material or a transformation into a different technology that performs the same function. So one of the challenges that we feel and that I think others who are doing this sort of work feel is first doing it in a defendable way so you can say with a good deal of confidence material A is of more concern than material B, and then finding ways to get this to the product development teams that are making the next generation of cell phones or aircraft engines or medical imaging machines so that they can make their materials selections with a knowledge of the possible constraints that may occur in the next decade or two.
Well, can't we develop man-made substitutes for some of those? Isn't that what we've done in the past when we've come up against scarcity like this?
We often have. We haven't always been successful at that. And I think among the challenges that we have are that as we use materials in a much more precise way than we have in the past and under much more stressful conditions, we restrict the range of possible ways around a shortage of material. A jet engine on an aircraft is perhaps an example. In the combustion chambers of those engines, the turbine blades operate at very high temperatures, 1,300 degrees centigrade or thereabouts. And there are few materials that are capable of of maintaining their performance and maintaining corrosion resistance at those temperatures and at the pressures they operate under. So we are challenged by the fact that we want our jet engine to operate very efficiently so that it burns cleanly and doesn't generate pollutants and generates a lot of power, and that means high temperature operation, and that means a very small number of metals formed into alloys that work very precisely at those temperatures and pressures. There are analogs of the same sort of challenge in some of the other things I've mentioned in modern electronics, in the medical field, and so yes, the general science and engineering community is trying to develop new ways to do these things. There are real challenges there, and because the idea of criticality and potential constraints on materials is a fairly new one, many of the product development teams that are working hard to design and manufacture new products really were never trained in this area, don't have any background in it, and unless they happen to be listening to your program or other things like that, we may not be able to communicate very effectively with them. So that again is part of the job that we have ahead of us, is to do this job well and communicate it very broadly to the people that are the ones that are saying to their suppliers, I want so many kilos of this material and so many kilos of that material, and I know why I do.
One of the articles that I read about this study mentioned that there's a bill, I think, being presented in the U.S. Senate that would designate a list of up to 20 critical minerals, and it would spend $60 million to conduct an assessment of their scarcity. It would also speed up domestic mining if necessary, and it would fund research into alternatives. You've heard of that, I assume?
Yes, I have.
Any thoughts on it?
Well, I think all the parts of it are easily supportable. The total use of materials is enormously more costly than a bill to do the things that you mentioned, and I think a lot of good would come from supporting investigations into this area that are more than a research team here, a research team there, that might not necessarily be very well coordinated or might not have the interests of North America so much at its heart. The Europeans, I think, as a continent, are probably ahead of us on this, partly because they themselves have so little these days in the way of resources. So I think the bill makes a lot of sense. There was a hearing 2 or 3 weeks ago in Congress where several people testified in support of it, nobody against it. This is a rather difficult time to predict whether the U.S. Congress will accomplish any particular thing.
Indeed.
So,
I'm sorry, sir.
So I really can't anticipate the outcome of this, but it would seem to me to be one of the easier things that has strong bipartisan support, and on the scale of governmental costs, a fairly low cost. So I'm hopeful, cautiously optimistic, I guess I'll say.
Well, it's interesting. I actually thought that most of the articles that I read about this when it came out a few months ago were fairly even-handed, even if the headlines weren't, because they did use the words irreplaceable a number of times, which is, again, vaguely terrifying. They could have been far more alarmist than they were. So did you find that your study was covered in a way that was true to your results?
Yes, I think so. Many of the factors that we have to take into account are not very well quantified. The geologists have trouble estimating exactly what might be economically extractable from deposits in the ground, partly because it's fairly difficult to really estimate those carefully without an awful lot of drilling, and drilling costs money, and you don't just do it willy-nilly. So we're a little short of geological data. The geopolitical data are available, but geopolitics is unpredictable.
That is not a science, yes.
And there are some aspects, as we were talking earlier, where the data just, even though in principle they should exist because somebody knows each piece and somebody else knows other pieces, for proprietary reasons, the information just isn't publicly available. So I think we can make pretty good estimates of the situation, but we can't be definitive at this stage and probably will not be for quite a while to come.
Well, then maybe I'll ask this in a very specific way. How concerned are you about this, honestly? And feel free to use a 10-point scale if that helps.
It's my anticipation that over the next, say, 20 or 25 years, we are likely to find 3 or 4 or 5 metals that will not meet the criterion of being available in reasonable quantity at an affordable price in a reasonable amount of time. I can't, however, predict which ones those might be, because that will depend a lot on how technology evolves, what new supply and demand challenges there are. But I think there are enough warning signs hovering around this issue that it is unlikely we're going to get away without running up against 2 or 3 real challenges over the next 2 or 3 decades.
So I shouldn't go back to being terrified, or I should?
I think you should be not terrified. You shouldn't assume there's no challenge here. I think you should be cautious and keep your eye on this topic, because it's one that evolves and issues will emerge that we aren't taking into account at this point. But what we, I believe, have come to as technology has grown, as people have become more abundant, as their wealth has increased, we're pushing the system in a lot of different ways, and sooner or later it's going to let us know that we can't assume that there's an infinite amount of everything.
Well put, sir. Thomas, thanks very much for being here.
You're quite welcome.
We've linked to Thomas Graedel's study in the Proceedings of the National Academy of Sciences, and the study is called The Materials Basis of Modern Society, and that's linked on our site at scienceforthepeople.ca. And we'll be back with Moses Chan to talk about where we stand with helium after these messages.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
This is Science for the People, and I'm Desiree Schell. I'm here with Moses Hung-Wai Chan, the Evan Pugh Professor of Physics at Pennsylvania State University. He's a member of the Committee on Science, Engineering, and Public Policy of the National Academy of Sciences, National Academy of Engineering, and the Institute of Medicine. He's served on a number of committees convened by the U.S. National Academy of Sciences, including the Committee on Responsible Science and the Committee on Understanding the Impact of Selling the Helium Reserve. Thanks for being here, Moses.
Oh, thank you.
Okay, now you and I are here to talk about whether or not we're running out of helium. So let's give some backstory here. What are we currently using helium for?
Helium is used in a variety of purposes. The most prominent is probably for cryogenics. And for example, a lot of us go to do MRI, and MRI machines need very high magnetic field. In order to have high magnetic field, you have to bathe the superconducting magnet in liquid helium at very low temperature to provide the stability of the magnetic field. And cryogenic currently constitute about a quarter of the usage for helium. And of course, helium is also used for scientific research, because we want to go to low temperature, and sometimes use it to have high string magnetic field, like in the particle accelerator at CERN, people may have heard about, but also for benchtop scientists like myself and others, just want to go to the extreme temperature to find out how the effect of quantum mechanics work And it is also used for propulsion of rockets, because helium is a lot of rockets use liquid fuel, namely burning hydrogen with oxygen, and helium gas is actually used to push the oxygen and hydrogen to be burned together. And also welding, diving, water balloon, and a very large variety of uses. Oh, by the way, also for making integrated circuit and also for fiber optics. So it is extremely important in all aspects of our life.
Why might we be running out of it?
Strictly speaking, we're not running out, but it is running out for, well, let me step back. Where are the helium? Helium are found together in the natural gas wells, in some natural gas wells. And for example, near the Texas Panhandle area, there is the one that was discovered in the early 1900s, and was found that the natural gas have something close to about 1% of helium. And the U.S. government, particularly at that point Navy, after they strip off the natural gas, send it to pipeline, they store the helium gas. And because at that time the U.S. government was building airships, and we need helium to float the balloon because it is much more preferable than hydrogen, as we know about the Hindenburg. And it is also found in other gas wells in Russia and also in the Middle East. Not all gas well has helium gas, and therefore, in order to what we call refine the helium, it causes energy, causes money, and to refine the very small quantity helium to be pure helium, and then also liquefy it to be used for cryogenic purposes. As the industrial use and also the MRI use actually increases very rapidly, it is putting a strain on the market. For the last 30 years, because ever since 1960, the U.S. government had been buying the helium gas from the natural gas producers. So the U.S. government has a large stockpile. But in 1996, the U.S. Congress said that the Bureau of Land Management, which now has the duty of keep the stockpile, have to sell off the helium. So the U.S. government would not get into this business. Therefore, helium become a commodity, much more, just like other commodity, will be subjected more to the fluctuation of the supply and demand. In the past, the U.S. Helium reserve provided close to really 40% of the world market. And this will be slowed down tremendously in the next next year, really, because we are supposed to stop selling it by the year 2015.
If it's possible that, well, as you say, that we are running out in a lengthy way, but still running out nonetheless.
I'm sorry. Yeah.
Why is the cost of it still so low? That's what I don't understand. Because if we're still using it for kids' balloons, usually scarcity drives the costs up, correct?
Actually, yes. The balloon industry, I forgot to mention the balloon industry. I do not know the number. I guess it's reasonably high, like 2 or 3%. But the kids' balloons situation is a bit more complicated. Although helium is expensive, right now, if I think I did the calculation once, the amount of helium in the balloon, if you use the so-called cost from, if you look at gas cylinder, the amount of helium in the balloon costs only 2 pennies. And therefore, the cost of the balloon is not in the helium. Therefore, even if you double the price of the helium, unfortunately, that is not a disincentive for people to put it in the balloon or things of that sort. However, helium for some other people, like, for example, for scientists, it is a very large cost because a typical grant given by US government, like NSF, or in Canada by NSERC, for people used to do experiment at low temperature, the helium, liquid helium cost is easily 30% to 40% of the total budget. Therefore, if you increase it by a factor of 2, that will basically squeeze out any possibility to do the research, because then you have no money to provide other needs like supporting the graduate student who are living on poverty wages anyway. So that, therefore, the cost of helium is a very interesting subject. It affects most the scientists at this point. Another thing perhaps important is the welding industry, because they use it quite a lot. And the effect is starting to have effect on the welding industry and aerospace industry, because, by the way, helium is also used for leak testing. If you want to build an airplane or something like that, you want to make sure that it's not leaking, and helium is very convenient to be used for leak testing. And in the past, some of the industry may not conserve it. So in other words, it's so cheap, they just use it once and get rid of it. But now, it is my understanding now, there are more incentive to recycle the helium to use it again. Even for MRI, helium is quite expensive, but compared with the cost of the technician, the cost of the people reading the MRI, and the machine itself, helium, even you double the price, it is still not changing the economic very much. So that is one of the reasons that we have not been doing as much recycling as we should be.
You're listening to Science for the People, and I'm talking to Moses Hung-Wai Chan, professor of physics, who has served on the U.S. National Academy of Sciences Committee on understanding the impact of selling the helium reserve. So why exactly can't we produce more?
We can produce more. It is very likely that there are other natural gas wells will have helium, but their amount will be a lot less than 1%. Say, for example, roughly speaking, if you have a gas well has only 0.1% of the helium, the cost in recovering will be very high. The reason is we do not go and actually just produce helium from the natural gas well for the sake of helium. We actually want the natural gas. Therefore, helium is just another byproduct, and that it is a very valuable byproduct. And therefore, in gathering the natural gas, we also can and extract the helium from it. And right now, for example, the helium from the Algeria and area, and also particularly Algeria, although the gas well there, the amount of helium in the gas well is the percentage is very low. If I understand, it's in fact only 0.3%. But it is economically viable because over there the natural gas liquefied to be liquefied natural gas. Therefore, in the process of liquefying natural gas, you are more than halfway there to liquefy helium. Therefore, even though the amount of helium in the gas well in Algeria is quite low compared with the US, it is still economically viable. Right now, the only gas well in the U.S., because U.S. do not ship natural gas liquefied natural gas by the pipeline. So the only gas well that is economically viable at the price that we are paying, which is on the order of $5 a liter of liquid, which is, I suppose, a bottle of cheap wine, then only natural gas well with helium close to 0.5 to 1% is viable. And so as time goes on, the amount of helium produced in the US, possibly also Canada, will be going down because we don't have many gas wells that's rich in helium. We know that there is a lot of natural gas in the area where I live, Pennsylvania, Ohio, and New York, but the natural gas from the shell, from the Marcellus shell, has no helium. So that is also a potential worry, because if the U.S. Canadian population can have enough natural gas and cheap natural gas without helium, that means that there's no need for the natural gas. There's less of a need to have natural gas from the Texas Panhandle area that's rich in helium. So it's very likely the helium price will go up in the next few years.
So is that going to be the biggest impact, is just the cost? Are there any other practical impacts?
Certainly, we should also worry that the committee we were in, we try to emphasize conservation is important. In other words, if we continually use helium at the rate we are using from the natural gas well that's currently producing helium, the amount of helium will only last about 30 years. And so if we're willing to dig deeper, so to speak, and try to develop a natural gas well with a lot less helium, with a much higher cost, well, just like fossil fuel, it is possible that the amount of helium we can use will extend the lifetime that the helium that we will have. And however, because we do not recycle it, helium just boil up to the atmosphere. By the way, it is true that we have lots of helium. There are lots of helium in the atmosphere, but that is only on the order of 0.1 part per million. Therefore, if we want to extract the helium from the atmosphere, it's possible, but the cost will be astronomical. And the need in the future for our industry, for scientific research, for medical use, and all that, the need for helium will increase. And so that is a concern, that how do we provide the supply to satisfy the demand? And it seems natural to us that the large users should follow the lead of the scientists. Scientists as a whole, the total usage for scientific use for helium for the whole world is on the order, it's difficult to estimate, but it's close to 2 or 3%. But the amount of 2 or 3%, the amount of helium that is recycled by the scientists is very high, because a lot of times that we are forced to, because as I explained earlier, the cost of helium is a large cost for the scientific use. Therefore, I would estimate close to 60% or 70% of helium are being used and reused again. We can recollect the gas, liquefy it, and use it again. It is our hope that the industry will follow our lead to recycle the helium. We don't think that for use of shooting up rocket, if you use liquid fuel rocket, I think that will be very difficult to recycle the helium. But industrial use certainly can go a long way in reducing the net loss by recycling helium.
So then is there any point for non-scientists, people like us? Should we stop buying balloons, or is that not even going to make a dent at this point?
It's very important to keep our children happy, have a happy birthday. It's very important. As you know, the other choice of you make a balloon float, it will be hydrogen. And hydrogen and birthday candle does not mix. They don't mix very well. And so we understand the difficulty, but I believe there are some so-called balloon gas is using a mixture of helium and hydrogen and an inert gas like nitrogen. You can mix it up and reduce the amount of the helium in there. I would say, well, I don't know what to say. I don't want to be such a bad person to say no birthday balloon, but maybe we should be conscious about that a little bit, because, as I said, the economics may not be the driving factor for quite a while.
Well, that might be self-solving if balloons are $10 a balloon.
Well, yes. But I just want to remind you, but right now, the balloon, most of the costs are actually the skin of the balloon rather than the gas inside at this point.
Moses, thanks very much for your time.
Thank you very much.
We've linked to Moses Hung-Wai Chan, the Evan Pugh Professor of Physics at Pennsylvania State University, on our site at scienceforthepeople.ca. You're tuned in to Science for the People, and we'll be right back with James Elser to talk about what we do without phosphorus after this.
On the next episode of Science for the People, we're learning about some of the most fortunate accidents and fascinating personalities in the history of science. We'll talk to astrophysicist and author Mario Livio about his book Brilliant Blunders, From Darwin to Einstein, Colossal Mistakes by Great Scientists That Changed Our Understanding of Life and the Universe. And we'll talk to historian W. Bernard Carlson about his book Tesla, Inventor of the Electrical Age. That's next week on Science for the People, on your local radio station, or online at scienceforthepeople.ca.
Welcome back to Science for the People. I'm Desiree Schell, and next up in today's episode on things that we might be running out of, I'll be talking to James Elser about phosphorus. James is a Regents Professor and Parents Association Professor of Ecology, Evolution, and Environmental Science at the Arizona State University School of Life Sciences. He investigates the theory of biological stoichiometry, the study of the balance of energy and multiple chemical elements in living systems. He and his international team of collaborators seek to understand how the coupling of carbon, nitrogen, and phosphorus shapes the ecology and evolution of living things. Very good to have you here, James.
It's great to be here and talk about my favorite element.
Now phosphorus, which I assume is your favorite element, plays a fairly massive role in modern industrial agriculture, correct?
It's played a massive role in all of the history of life since things first got rolling. But yeah, we now use something like 23 million metric tons of phosphorus fertilizer every year to support our current agricultural system.
So then what does phosphorus do exactly?
Well, it's a very important component of many important molecules. The most important one that everyone knows about is DNA. So phosphate, we like to say that phosphate or phosphorus holds your genes up. It's actually in the structure of DNA itself. It joins all those A, T, C's, and G's together in a string. And so without phosphorus, we can't make our genes. We can't make the machines that make proteins because they're made of RNA, which also has a lot of phosphorus in it. It's a chemical cousin of DNA. And so plants and microbes obviously need those DNA and RNA. So do we. But we also need it not just for our DNA and RNA, but also so we can sit up straight in our chair. That is, phosphorus is in our bones, makes up the mineral apatite, A-P-A-T-I-T-E. That makes up our bones.
Well, okay, so that sounds Even more important than its use in fertilizer.
Well, its use in fertilizer keeps that whole food chain going, right? So we get a lot of crop yield. High crop yields require high phosphorus availability because those crops are growing fast and making a lot of proteins and making a lot of biomass. And then we need to have enough phosphorus in the food itself that we eat and our livestock as well so they can make their genes, make their DNA, make their RNA. And in the case of chicken and poultry and livestock and humans, we need to have enough phosphorus in our food to make our bones.
Well, then what's the process by which we turn phosphorus rock into something that we do use in fertilizer?
Yeah, so right now industrial fertilizer relies almost entirely on mined phosphate rock from a few areas of the world. These are ancient geological deposits that lay down hundreds of millions and tens of millions of years ago in shallow oceans, where they formed phosphorus-rich sedimentary rock, usually. Some phosphorus that's mined comes from volcanic or igneous deposits, but most of it comes from these sedimentary deposits, which are very ancient. So we dig those up. We treat them with concentrated sulfuric acid, which replaces the phosphate with sulfate. We get a concentrated form of phosphorus out, usually in the form of phosphoric acid, which is then reacted in different ways to produce the final TSP, triple superphosphate fertilizer you can get at the store, or mixed with nitrogen and potassium to make the NPK fertilizer you can get at the garden store. And these are things, of course, that farmers buy from various suppliers to add to their fields every year. So that's a long process. They have to dig a lot of dirt up, a lot of rocks up, grind them up, pound them up, treat them with acid, end up with a big pile of something called phosphogypsum waste left over. There are big piles of this around all the phosphate mines of the world. Contains a lot of radon. It's sort of unpleasant stuff to live nearby, and this is why a lot of the phosphate mines in Florida are slowing down, because no one really wants a big pile of phosphogypsum next to their golf course anymore.
Right. So why is there concern that we're running out?
Well, the word running out is interesting. We're probably never going to run out of phosphorus in the sense that Earth will always have as much phosphorus as it ever had. It's sort of different than petroleum where we're burning it, right? So phosphorus is not destroyed when we use it. It just goes somewhere else in a less concentrated form. What we seem to be running out of is the cheap stuff, the easy stuff to get. And then this is manifested by people got serious about this in 2008 when there was a 700% run-up in the price of phosphate rock that sort of got everyone's attention and led people to wonder whether we were coming up against scarcity limits on the availability of phosphate rock for fertilizer production. So that got a lot of people's attention. So I think it's better not to talk about running out of phosphorus, because we won't. We might well be running out of the cheap stuff, though.
Well, and there's a lot of variables around the scarcity that you were talking about, a lot of things that could potentially impact our phosphorus reserves, right?
As far as demand is concerned, or supply?
Supply. I'm just thinking things like the growing global population.
Well, that's the demand side issue, right? So so population is growing. Or maybe, the UN projects we could be anywhere between, I think the low end estimate is 7.5 billion. The high end estimate is 13 billion by 2050 when the human population will peak out. Then what we really want to be doing between now and then is raising per capita food availability. That is to raise the food security of, especially those people sort of at the bottom end of the socioeconomic distribution right now. And generally the estimates are food availability at least needs to increase by 70 to 100% between now and 2050. So that's going to potentially involve a lot more demand for food and food production, a lot more demand for fertilizer inputs. And so that's going to put even more pressure on the phosphorus supply system. The other thing that's going on that's actually sort of good news is that people are generally becoming more affluent now. This is happening in China and other places around the world. And when people get more affluent, they add meat to their diets. Right. And meat is a very phosphorus-intensive process because we have to grow the crop. We have to put phosphorus on the crops that we then feed to animals. And then a very little of that is transferred up. And so there's a lot of phosphorus lost at the first stage of growing the feed crops, and then the second stage in the manures and excretion from livestock. So as more and more meat goes into the global diet, the phosphorus footprint of the global population goes up, and that's another pressure. And the other thing that's going on is biofuels. So we're trying to solve our carbon problem. We now know that we have a carbon problem in the atmosphere, so we're trying to generate energy without burning petroleum and substitute biofuels for petroleum energy, which seems like a great idea. On the other hand, all those biofuels will also need fertilizer, and we're now working to estimate the fertilizer demands that might be needed if we were actually to go to a biofuel-based energy economy. And those demands are quite enormous, might be the same magnitude of what's currently used for food production, and that's another pressure on the phosphorus supply system.
What about substitutions? Is there anything else that we could use instead of phosphorus, just in case?
No.
Good.
Because, well, you remember there was that controversy a while ago about that weird bacterium that
Right.
might be using arsenic instead of phosphorus. But it turns out in that case doesn't even seem to be true, even in that trivial little microbe. Every living thing uses phosphorus in its DNA, its RNA, etc. So we're not going to be able to do without it. We can develop, though, probably more phosphorus-efficient crops, and people are working on that. We probably won't develop more. Well, I guess, there's this old Gary Larson cartoon of the rubber chicken ranch where, the chickens are sort of draped over the scenery and the signs because they have no bones. I suppose if we had poultry that had no bones, we would develop a low-phosphorus poultry industry, but that also seems quite outlandish. So the issue with phosphorus is it really is not substitutable in its fundamental functions. So it's not like these other metals that are used in electronics where you might be able to get by with one or the other for the same function. In biology is very serious about its commitment to phosphorus in biology. On the other hand, we can substitute more efficient processes and approaches for inefficient ones. And that's what a lot of people are working on, just doing a better job with what we have and how we handle it.
You're listening to Science for the People, and I'm here talking about why we should care about a potential phosphorus shortage with James Elser, a Regents Professor and Parents Association Professor of Ecology, Evolution, and Environmental Science at the Arizona State University School of Life Sciences. Okay, so how serious is this at this point? I understand we're going to have to potentially put a lot more energy into producing phosphorus, so how will that affect us?
Well, the problem is not acute right now here in the happy developed world, where fertilizer costs are not a huge part of what farmers have to pay to run their operations. So if even at our current prices now of phosphate fertilizer, which are about 200 to 300% higher than they were about before this whole thing started in 2006 or so. So if right now it's not a big deal in the developed world, but in the developing world, especially sub-Saharan Africa, where most of the world's undernourished people are living, many of them are living, small stakeholder farmers growing crops on poor soils, phosphorus-deficient soils, they need phosphorus fertilizer to raise their yields so they can feed themselves. And then that's where the demographic transition needs to take place, where birth rates will need to decline in response to greater prosperity and food availability. It's the normal sort of thing that happens. If that can start to happen, we can hit that 7 billion peak or 8 billion peak human population instead of the 13 billion one in 2050. Those farmers can't afford fertilizer right now at the current price. And so the worry is that 30 years from now, 40 years from now, things continue along the road we're going and phosphate prices go up again or stay high, we won't be able to achieve food security for those people. And so that's the main concern that I have in all of this. The other side, though, is the other part of this is the downstream side of phosphorus. So phosphorus has been so cheap that we tend not to worry too much about it on the farm. So we lose a lot of it downstream in irrigation ditches and erosion. We lose a lot of it on livestock rearing operations and manure and whatever. And when it goes downstream, it makes a big mess because when it gets into a river, a lake, or a coastal ocean, it stimulates the production of algae and other nasty plants and such. And you get green eutrophic lakes and fish kills and dead zones in the coastal ocean. So we think that what would be great, and as we move to a real phosphorus cycle in the human food system where we recycle much of the phosphorus that we then use as fertilizer instead of digging it up somewhere else, we return it from sources inside the system. Once we get that operating, we're going to not only have a more sustainable, resilient, and long-term reliable phosphorus supply, we're also going to have clean lakes and oceans. And so we think that's the other dimension that makes a lot of this very attractive and feasible going forward.
Well, see, that sounds like a great idea. So is anybody working on implementing those suggestions?
Yeah, there are people starting now to develop different sorts of approaches. There's now commercially available phosphorus recycling approaches that are implemented in advanced wastewater treatment plants, and where commercially useful fertilizer is produced and sold. That technology has not gotten widely distributed yet in wastewater treatment plants, but it's getting going. People are inventing new things like new toilets. Like Switzerland, they invented something called the no-mix toilet, because what you want to do on a toilet is keep the yellow stuff away from the brown stuff, because the brown stuff has got a lot of the pathogens in it, and it's the nastier bit. The yellow stuff is clean, it's sterile, it's almost ready to go. And so there are various technologies being developed at the household level or the neighborhood level or the building level that will take advantage of waste source separation to recapture phosphorus and nitrogen in urine in domestic situations. In the developing world, the Bill and Melinda Gates Foundation just sponsored a Reinvent the Toilet competition, and part of the winning entry does involve recapturing fecal and urine phosphorus and nitrogen and sterilization of that for production and recycling as fertilizer. There's a whole movement that is involved and has been working on this for quite some time. It's called the Ecological Sanitation Movement, which seeks to deal not only with the phosphorus and nitrogen side of the issue, but also the human health dimensions from inadequate sanitation. So develop feasible, deliverable sanitation solutions that solve the infectious disease problem, as well as the fertility problem and the fertilizer issue. So those are things that are going forward. Food waste, that's another thing. So we waste about 40% of all the food that's produced now, both in developed and developing world. That amounts to about 5% of the total amount of fertilizer that's applied annually. So people are inventing something called anaerobic bioreactors. These are vats in which you dump food waste, or you can dump manure in them as well. And then you unleash the power of the microbial world on them that then digests that good organic matter to get at its energy. Because it's anaerobic, these creatures will produce waste materials in the form of methane and hydrogen gas, which can be captured and burned as a form of bioenergy. And then at the end, there's a concentrated solution of phosphorus and nitrogen available that can then be used as fertilizer. And we envision a world where anaerobic bioreactors are out in people's neighborhoods. They're out in restaurant districts, they're out behind your grocery store, and they're out in dairy farms, and they're out in livestock operations to recapture nitrogen and phosphorus and return it to agriculture, and they pay for themselves in the bioenergy that they generate.
Well, until then, is there anything that individuals can do?
Yeah, a couple things. One thing you might want to consider, and it'd be good for your arteries as well, is to eat a little less meat. So move a little bit lower on the food chain in your diet. So, I'm not a vegetarian, but I admire people who are. I do try to eat vegetarian as regularly as I can, a few times a week. Different forms of meat have different phosphorus footprints. Beef is the most phosphorus intensive meat that we consume. It's also the most energy intensive, so a little less beef would help. Pork is better. Chicken is better than pork. And so shift in that direction would help lower your phosphorus footprint as an individual. Ask yourself whether you really need that lawn to be that green, because there's a fair amount of fertilizer that's used in lawn maintenance. Mm-hmm. So converting away from a super big green lawn to just a little patch you actually use might be useful. Make sure your septic tank is maintained, because a lot of phosphorus leaks out of inadequately maintained septic tanks and gets into water and causes pollution. We need to reinvent the septic tank as well, by the way, in order to recapture that nitrogen phosphorus rather than just burying it in the ground behind our house or going to wherever the truck that pumps your septic tank takes it.
James, you do super interesting work. Thanks very much for being here.
All right. Well, remember to save the P. And that's what we got to do.
Okay, start there. You have to.
We have to save the P. That's one of our slogans. And the P is spelled P-E-E.
I would like to go back to my previous comment. You do very interesting work, sir.
All right. Thank you so much.
And we've linked to James Elser and the Elser Lab on our site at scienceforthepeople.ca. Science for the People is recorded in Edmonton, Alberta. The show is produced by Rochelle Saunders. Ryan Bromsgrove is our promotions manager. Our social media manager is Chelsea Butler. K.O. Myers updates our website. Helen Quivalon is our publishing liaison. Ed Haynes is our guest coordinator. We get research help from Josh Witten. The show is edited by K.O. Myers and Ryan Bromsgrove. Our theme song was written and recorded by Fractal Pattern, and its title is Binary Consequence. The show is hosted by Rochelle Saunders, Marie Claire Shanahan, and me, Desiree Schell.